Okay, so we can start here. So from the last session, we covered the interpolation. And regarding the interpolation, we did the Lagrange interpolation, the Newton interpolation, and we left, the last time that we had class together, we were discussing about the spline interpolation. Now, regarding the spline interpolation, I would suggest to go over the textbook again, and I'm going to share another recording, probably I'll share with you later. But but I hope that once you see that those notes or the material that I'm going to share with you, I hope that also this last part of spline interpolation would become clear. Okay? Interpolation. Now, after the interpolation, the next chapter that we're going to move on, it's going to be numerical integration. So we have here NI, or numerical integration. And when we talk about numerical integration, it's going to be the numerical approach to the analytical approach that we have used in calculus, that we have seen in the first year of your bachelor studies. And something which will become useful regarding the previous topic, spline interpolation, is going to be the numerical differentiation. Now, I'm just mentioning this right now so that, because we won't come back to this one again. So this spline interpolation, it will become very useful when we talk about the numerical differentiation. Okay, so this is Ni, and this is going to be Nd. So when we start with the numerical integration, the general idea is the following. So we have a specific function, and we want to find the integral which can be expressed by such a function, fx dx. Okay. Even when you started the integration in calculus, most probably you have started by analyzing it as a sum over specific terms. Okay, so you were calculating some limited delta x, and the idea is that to calculate the area here, there are quite a few approaches, which is where one of them could be, let's say, to define an integration either here. So one approach would be to use this value of the function and to calculate the area here in black. Or you could also use this one by using the other value of the function and calculate this area. Okay. So this will be the partial integration in this region. Now we are going to use a similar approach. And the similar approach that we are going to assume is going to be something, so the approach that we're going to use, it will be we're going to assign a polynomial to the region of interest. Okay, so we're going to assign, let me call it this way, a polynomial. And now, today, we're going to see a couple of different numerical integration techniques, and the essence in all of these integration techniques, it will be the Lagrange interpolation. So we covered when we covered the interpolation chapter, we discussed the Lagrange interpolation, and that will help us to define the relevant polynomial that we are going to use. Now, let's say, let's assume that we want to find the integration of the integral of this function from this point here, x0 to xn, or x1. Or let's call this a to b. Okay, so let's assume that we want to find the integral from a region A to a region B, and meanwhile, okay, I think we're good. I just have to check something. And the simplest approach that we can use, that we're going to see very soon, would be to approximate this whole function with a linear function. Okay, it would be even simpler by using probably the value of the function like this. So we could use a constant. So the first approximation of this integral, which is this one here, would be, well, the first approximation would be if we use f of a times b minus a. Okay, that's an integral. We get this area, which we show here in red. And then the next approximation, it could be the following. It could be, we draw a straight line here, and then the area of this trapezoid, we know how the area of the trapezoid is a small base plus the large base times the height divided by 2. So this could be, so we assume that the trapezoids, they stand like this. So how is the area of this trapezoid? We know that we can assign, so this can be base 1, base 2 height, and this is B2, B1 height again. So the total area is B1 plus B2 times height, but then we have to divide by 2. So when we come to this case, this is going to be something like this, f of a plus f of b, so which means that this height, which we see this here, plus this height here, times the b minus a divided by 2. Okay, so this is another approximation. Now, let's see how many points did we use in here. So here, it looked like we used the information of only one point. So the number of points here, let's call this NP. Number of points that we consider, it's 1. And what is the polynomial Pn of x? What polynomial is this? F of a. Can someone answer for me regarding this?
0-degree polynomial.
So in the first case, what was this f of a? What polynomial is this? This is a polynomial of 0th order because it's a constant number. Okay. So this f of a, the value of this function at this point a, is 0th order. So we call this 0. Number of points that we used, it was 1. We use a polynomial of 0th order. If we use this other approximation, which most probably is slightly better, but it's going to assign, it is going to add this area to the previous area, which we try to draw this in red. So now, we use a different approach. So we assume that, and how many points we used here to find this new integral? We used here 2 points. We used point A and point B. So if we use 2 points, the polynomial that we came up with, it is a linear polynomial because the line which is joining these 2 endpoints, A and B, it's of the first degree. Okay? We know that the first degree polynomial, we can draw a straight line. So here we have a polynomial of the first order. And now assume that this expression, what we can do is that we can assign a third point, A, B, C. We can assign also a third point here. And if we have a third point, which means that we have here, this one here, this one here, and this one here. Now, if we have 3 points, what polynomial can we assign there? We can assign a polynomial of the second order, okay? So if we have 3 points, number of points 3, we can assign a polynomial of second order, and so on. So, and we know that functions that might even oscillate, it's easy for us, not easy for us, it's better if we use a polynomial of a higher order. Now, this will be the approach that we are going to use, okay? And let's start. We can start from the simplest, of these cases, and probably we'll start at this specific case. And the first set of numerical integration techniques They are called Newton-Cotes formulas. Newton-Cotes formulas, allow me just for a second as I pick up one material that I want to share with you. So Newton-Cotes formulas, we are going to see together three different techniques that use Newton-Cotes. The spatial condition regarding the Newton-Cotes is that this interval over which we want to integrate is going to be equally spaced. So what we see here, we're going to keep the interval like AB as it is here. Then we're going to, meanwhile, I'm trying to download something. Then we are going to separate the interval in 3, 4, 5, or 6 different intervals. But special about those is that all of these intervals, they will be equally spaced. Okay? So this is something very special about this. And the techniques that we are going to see here is that we're going to see one, trapezoid techniques, which somehow we did it here because we approximated this function that goes like this to a trapezoid. And then the next technique that we're going to see, it will be the Simpson method. The second one is Simpson method. And this is called Simpson 1/3 rule. Okay? Simpson 1/3, and then we will have Simpson 3/8. Okay? This has something to do with the coefficients that we have to use. Okay? And now, when we and for each, now I want a feedback from you. If I turn on the light, can you, will the view be better or not? Because I'm afraid that the reflection might diminish the quality that you see. So
it's
is
better
it better
now.
now?
Yeah, it's better.
Not bad. I mean, but I'm afraid here we get some reflection, but because I don't want to okay, if you have any comment, I can turn on the light again because anyway, this is a small glitch or a small comment. Now, so we're going to see this Newton-Cotes formulas, and let me see. Okay, so the first thing that we are going to see, it will be, as you can see from here, the Newton-Cotes formulas. We have a polynomial fit between the points. If we use 2 points, we can construct a trapezoidal rule. This is how we call it. Then if we have 3 points, then we are going to have the Simpson rule, but as we wrote it on the board, this is called Simpson 1/3 rule. And the third, if we have 4 points, we're going to use Simpson 3/8 rule. And then we're going to see also another type of integration, where we are going to use the Richardson extrapolation. And now, these rules that we mentioned that n equal to 2, n equal to 3, and n equal to 4, you can easily notice that when n is equal to 2, we can have only one interval, okay? If the n is equal to 3, that means that we have 3 points, but we have 2 segments, okay? So we have 1 point in the n. So this is the function, and we have 1 point A and 1 point B. So if we use the second technique, that means that we have 3 points, but if we have 3 points, we have 2 segments. But always there should be equal segments. And if we have then, that means 2 segments. If you have 3 segments, we're going to use the last method. And the way where the Simpson techniques change between each other, it is shown in for example, if we have this Simpson 1/3, this appears because in the formula there is a factor h over 3, where h is equal to the width of a segment. Okay, so the width of a segment is h, and the n equal to 4, which means 4 data points, we have 3 equal segments. We have a factor of 3 over 8. Now, all of these 3 techniques, we can have the composite of these. So we can have CT, which means composite trapezoid. We can have composite Simpsons 1/3, CS 1/3. We can have also composite Simpsons 3/8. Okay. So the idea is that we're going to see it very soon what this means. And general idea is that we want to find an integral. That integral we approximate it with a polynomial of the order n. And the polynomial, it looks like what we see on the slide here. For example, if we have 2 data points, we have a polynomial of first order, then the equation, it will look as we see as the final result, where the integral, which will be approximated as fa plus fb divided by 2 times the width of the interval. Now here we have an example. If we want to use the trapezoidal rule, the function is given here. It looks like it's a polynomial of 5th order. Okay, and with this polynomial of the 5th order, we want to find the integral between 0 and 0.8. So it looks like if we assign what is the value of so between 0 and 0.8, I think this function, we have shown this one also on the slide. That's where we see it. So it is something like, it goes like this. So this is the 0.8 and this is the 0. Now, in this polynomial, if we substitute the value f equal to 0, the first point, we see that the value of the function, so f0, this is going to be equal to 0.2. And the value of the function when at the 0.8, it will be something different, which I don't have it here for a moment, but let me see. The value of the function at 0.8 is 0.232. So we have these 2 values, and then we have also the width, which we call here h is equal to b minus a. So this is the width of the segment, and it's equal to 0.8 minus 0. This is all that we care. Okay, so we substitute all the values here, and we find that the answer is equal to 0.1728. So the complete expression, it's going to be 0.2 plus 0.232 times 0.8 divided by 2, and the answer is going to be something like 0.1728. This is the integration, which in principle, this is going to be, so this area is going to be something like this. So the area that we are going to calculate is something like this, using the trapezoidal method. And it looks like it gives a pretty large error. Okay? So error is considerable. And for sure, we might expect a large order of error. Now, in this slide, at least what we see from here, we can also calculate the approximate error, and the error, it can be expressed as minus 1 over 12 times the second derivative of the function. So this function, if you see here, regarding the total error, it's evaluated at some psi, okay? Psi, it's a value which is between a and b. So this function, we can evaluate it at any point like this, and we try to identify the error. And the way to do this is that we get this function, which is a fifth order. We find the derivative twice, and if we take the derivative twice, the function is going to be what you see here on the slide, minus 400 plus 4x minus 10x squared plus 8x cubed. So with once we find this, the second derivative of this function, we find the average value. The average value of an integral, it is defined as, for example, this integral here is minus 400. So actually it's shown here. We integrated over analytically by having almost zero error. We divide it by the range and we get minus 60. Once we substitute this value, what we find is we see an error of approximately 2.56, which means that we found a value. So the answer, let's say the integral I, it was equal to 0.1728, 0.1728. But the error, it's approximately 2.56. Yes. Yes, any comment? Do we have any comment? Let's switch back to the... So this is how, so apparently we found this integral, and this error of 2.56 is going to be approximately this 2.56. It's a relatively high error, okay? Now let's see what our next slide tells to us. So from here, we can also construct a composite trapezoidal rule, okay? But at this part, I guess we can switch to the... So what you saw in the previous slide, it was that we tried to approximate the integral of this function, and we found like 0.17, which was this. And the error that we calculated using that expression is approximately 2.56, which most probably is this area here on top. Now, since this gives a large error, as we said before, we had composite rule, we had trapezoidal rule. Okay, let me write this here. This is trapezoid rule, and we can have also composite trapezoidal rule. We can have CTR. Similarly, we're going to see very soon that we can have Simpson 1/3 rule, and we can also construct composite Simpson rule. What this means, it means the following. If we need to find the integral between from 0 to 0.8, we can separate this one into one more, to add one more segment, okay? So now, instead of having a single segment, we have two. And if we have two now, that means that we can find the integral in this domain first, okay? Using, again, trapezoidal rule, by drawing the trapezoid that looks like this, and then drawing another trapezoid that is going to look like this, okay? And the reason that we call this is why we call this composite trapezoidal rule. And what we're going to see here is that the first area is going to be the value of this function evaluated at 0 plus the value of this function evaluated at 0.4. So we have 1 here. And for the other trapezoid, we have the value of the 0.4 plus the value at 0.8. So in principle, what we are going to see is that we have the values of the function here one time, plus twice the values of the function in the other regions. And the reason for this is that we're going to have f evaluated at 0, plus the function evaluated at 0.4, times h. Okay, let's keep this h here, where h, in this case, is equal to a smaller segment, okay? So let me add this here. H is equal to 0.8 minus 0 divided by 2. So H is very important parameter to notice, specifically when you go to more complex numerical integration techniques. So here we have H times these factors divided by 2. That's one part. And the other integral is equal to plus the function evaluated at 0.4 plus the function evaluated at 0.8 divided by 2. We multiply by H again. And finally, this is what we get. And we have some common factors, and we can write this again, like H divided by 2 times function evaluated at 0 plus 2 times the function evaluated at 0.4 plus the function evaluated at 0.8. Okay? So this is the idea. And H here, it's equal, so we should also know this here, that H is going to be it's 0.4, or at the same time we can call B minus A divided by 2. So in the end, this will be 0.4 divided by 2, 0.2. Okay? But what is something that we need to notice is that we have the functions are evaluated just once at the endpoints and twice at any new upcoming new point. Okay? And this is, so we try to evaluate this function again. So we have to find out what is the value of the function at 0.4. We have here, this is at 0.4. This is going to be equal to 2.456. So this is what we have, and then we come here, we evaluate the respective numbers. We get 0.4 for H, and then here, the function evaluated at f0 is 0.2, plus 2 times the value of the function here at 0.4, it's 2.456, plus 0.232, which is the last value. So with all this, the final value of the integral, we find 1.06, 1.0688. So comparing this with the previous result, this looks much more promising. So this was the previous result. Now the integral is approximated to being this. So it looks like the error, it has decreased a lot. And if we want to calculate the error, we can use a similar expression to what we had before, but it's a little more, it's going to be improved a lot. And this improvement, for example, just before a moment, the error, it was, let me find the expression. So the error initially, it was minus 1/12, the second derivative of the function, evaluated at any point midway through anywhere in this domain where we are calculating the integral, times b minus a, which is the whole domain, to the power 3. So this is the error which is expected from the trapezoidal rule. But now, if we have the composite trapezoidal rule, the expression, the error, it will change slightly. So for composite trapezoidal rule, this will be minus 1 over 12 n squared times this section remains the same, times b minus a, again to the power 3. So as you can see here, the error, so here, n, it corresponds to the number of segments. Okay, so n, in this case, n is equal to 2. We use 2 equal segments. And this error is going to be equal to what we had before. So here we can simply predict that the error is approximately what we had before. divided by n squared. So we get here 2.56 divided by 4. Okay, so this is how the errors propagate for this trapezoidal rule. And now what we move next? We move next to a little more complex numerical integration technique. So we go from the trapezoidal, we go to the Simpsons 1/3 rule. So initially, when we had just 2 points, A and B. And we had 2 points, so number of points it was 2, number of segments it was 1, and the polynomial it was first order, okay? Now we move to Simpson's 1/3 technique, where the number of points that we're going to consider will be 3. The number of segments is going to be 2. So I'm writing this one, number of segments is equal to 2. And then the polynomial, so let's write this Pn, the polynomial is going to be P2x. So it's going to be a polynomial of second order. And probably it's better if you write this one P1x, so with a polynomial of first order. So what happens here is that in principle, we have, again, we are forced for the points to be equidistant. Probably it would be best if we pick up some point which would correspond to some value which does represent the whole range of the function. So let's not forget the function is this one, that is the value of y, but we have to pick up a midpoint. So if this was from the previous example from 0 to 0.8, we are going to use 0, 0.4, and 0.8. And again, the way to derive this function, we use Lagrange interpolation, okay? We use Lagrange interpolation to predict it, and finally, the answer is going to be something like this. So the integral will be approximated as I is equal to h over 3 times the value of the function evaluated at the x0 plus 4 times fx1 plus fx2. So this is fx1 plus fx2, and let me have a look here in the. So I have a couple of notes in the slides, but probably we can have a look at those later. So I hope this is fx1, fx2. So this would be the integral. Now h is an important parameter, as we mentioned before, and this h will be equal to the width of the segment again. So we always look for this h, and this is going to be b minus a divided by 2, which means that if we substitute b minus a divided by 2, this integral, this will be b minus a divided by 6. Okay, because h is smaller. And then we have the same terms with factors 1, 4, 1. And if we try to solve the same exercise that we solved before a moment, so we had this function f of x, it was a polynomial of fifth order in x. Okay, so this is what it was. And now what we need to identify here is that we need to know what is the value of the function at 0, which we knew this before, and this was 0.2. Then we have to evaluate the value of the function at 0.4, which was equal to 2.456, and the value of the function at 0.8, and this was equal to 0.232. So the next thing that we need to do here is that we need to multiply the middle term by 4. Okay? So we just multiply this by 4, and then we add this up. Okay? So we sum all of these together. So we have this 0.2 plus 2.456 times 4 plus this, and once we find the summation, we multiply with b minus a divided by 6. Okay? So b minus a, it's 0, so we get all this total, and the answer here that after we sum these, will be multiplied with 0.8 divided by 6. Okay? So using this Simpson rule, we find that the integral in this case is going to be equal to 1.367. 1.367. Okay? And there is also an expression that calculates the error of this one. We're going to share this one just in a moment in the slides. But in principle, I hope that this was clear. Now, if you remember, in the previous example, when we use a simpler technique, and simpler, we mean that we have a much simpler polynomial, first-order polynomial. And as we know, first-order polynomial, they cannot match the curvature of complex functions. But second-order polynomials, they can do a better job. So for sure, this is it's way better, okay? But now, if you remember, we had trapezoidal, we had the Simpson 1/3. Now, let's construct the composite Simpsons 1/3. We call this one composite S 1/3. Now, with this composite Simpsons 1/3, let's remember, when we had the Simpson 1/3, we had the coefficients 1, 4, 1, right? Now, what we can do is that we can separate this interval a little further, okay? So the segment, so let's see, what is very essential here is the following. Well, let's separate this one. We have two segments, and immediately we are going to have number of segments is going to be 4, okay? If we divide this one just once more, if we divide this one twice more, this is going to be 8. But let's consider that the number of segments, the n will be still 3. We will still use, let's see here, this is 0.4. Now, we forget this part, okay? We look at the first part. We want to find the integral here. Using what? Simpsons 1/3. When we say Simpsons 1/3, that means that we have this 1/3 factor here. So let's have a look here and think simply. We have to define the next point, which is 0.2. And now, here, the coefficients that we will have to consider will be the following. So we have the first range here, and we have the coefficient 1 for 0, coefficient 4 for 0.2, and coefficient 1 for 0.4, okay? So this is how the first half is going to be. Then we move and we look at the other half, okay? We look at this part of the function. We start from 0.4 to 0.8. From 0.4 to 0.8, we need to do the same. What is the number of points? Number of points is 3. So we need the third point, which is 0.6. And then we have to find here the 0.6. And immediately, what we can think now is that if we are going to use the Simpsons 1/3 rule, what are the coefficients? The coefficients are shown here, 1, 4, 1. So then we apply here 1, 4, 1. But this one, the 0.4, is considered twice. So now in composite Simpson 1/3 rule, if we observe carefully the coefficients of all the points that we're going to generate, let's remember, these 0, 0.4, and 0.8, we had this before. we have now two new points, two new values, 0.4 and 0.2 and 0.6. And overall, we will have the following. We will have the coefficients will be 1, 4, 2, 4, and 1, okay? Because I think it's obvious from what we see here, we take this 1, we take this 4 times, we take this twice, because this value of the function at 0.4 is considered first when we take the first half of the integral, when we take this, and then the 0.4 value is also considered when we take the second half. So that's why we observe these numbers. And then what we need to do is that we have to evaluate the function at 0, the function at 0.2, the function at 0.4. Similarly, we go to the next point, 0.6, 0.8. So we have all of these values and respective values that are 0.2. This was 2.56, and this was 0.232. The new values that we have here for 0.2 is 1.288, 1.288, and then we have the other point is 3.464, 3.464. Now immediately we multiply all of these numbers with their respective coefficients. The first one is multiplied by 1, the second one is multiplied by 4, so the third one is multiplied by 2, this is multiplied by 4, this is multiplied by 1. After we multiply them, we add them together, so we find a total, okay? We find a total here, and this total will be multiplied by the h over 3. So this total will be multiplied by h over 3. But now, let me ask you, what is h now? Sash Danit? Can you help me here?
B minus A over 4.
Let me think. Let's think together about this one. B minus A, okay, over 4. That's the h. But actually, what was h before here? When we had a single Simpson 1/3 rule, the h, it was equal to half, because we had 3 points. It was b minus a. Now the h is going to be half of them, okay, which you are correct, is b minus a over 4. So we get here, we multiply everything with 0.8 minus 0 divided by 4. So this is h over, this is the new h. But then we have to multiply this also with the 1/3 coefficient, okay? Because this is called the Simpson's 1/3 rule. Now, so as we see here, we have where the Simpson's 1/3, the composite Simpson 1/3, and it looks like how many segments do we have here? Initially, we had 2 segments, right? Now we get 4 segments, and we can improve this technique a little further by assigning, I hope the different color is visible there. So if we use this in blue, we can still divide each of these small segments further, okay? And the number of segments, apparently, it will be odd, sorry, it will be even. So it can be 2, 4, further, you can get 8, and so on. What if we had an odd number of segments? So not 2, but let's say we had 3 segments, which means that we can have a case where, let's see at least the number of segments here. Now we're going to consider this one as a reference because this was a composite. So now we are asking the question if the number of segments was odd, or presumably let it be 3. Now, if we have 3 segments, that means that how many points do we need to consider for 3 segments? Three segments are defined by 4 points, okay? So we have 4 points. That means we have the 0 here, the 0.8. This is 2 points, we need 4. We got 1 here and 1 here. So only this way we have 3 segments. One is here, the second and the third. So it looks like we have to separate 0.8 by 3. And then, so NS is going to be equal to 3, but the number of points it will be equal to 4. Now, if we have the number of points are 4, what type of polynomial can we consider? Here, in this case, we are going to have a polynomial of 3rd order in X. And we know that second order polynomial do a much better job to track down the curvature of complex functions. And we can also for sure say that the 3rd order polynomial does a better job than a 2nd order polynomial, right? So we try to make clear these points when we were discussing about the interpolation, because in interpolation, the number of points, it helped us to determine the closest polynomial. So in this case, we can develop a Simpsons 1/8 technique. And because of this keyword 1/8, we will have a small modification in this expression, which we're going to provide right now. And the Simpsons 1/3 rule, using Lagrange interpolation, it provides for us that the integral here is going to be 3h over 8 times the function evaluated at x0, the first value, plus 3 times the function evaluated at x1, plus 3 times the function evaluated at x2, plus the function evaluated at x3. So this is the fourth point. Okay? So this is the new Simpson numerical integration technique. And this 1/8, it comes from the fact that here we have a factor 1/8. And the h here is going to be b minus a divided by the number of segments, okay? And the number of segments is equal to 3, right? So this is equal to b minus a divided by 3. So if we substitute here the b instead of the h, what happens here, this factor will be substituted. Allow me not to write the whole expression again, but this will be b minus a over 8. B minus a over 8, because this 3 will cancel this other 3. But looking at this expression, maybe it's good also, but at least for the reference, okay? It helps us to understand why it is like that. And now we look at this domain, and what is h, in this case b minus a over 3, is going to be 0.8 divided by 3. And this is something like around 0.2, 0.26. The next point, it will be 0.27. And the next point is going to be 0.53. And for sure, we have to track down the function, whatever the shape was, and we need to evaluate the function here, the function here, here, and here. And then we have to look for the coefficients. The coefficients that we're going to consider are 3 here, 3, 3, and 1. So I hope that the next thing that we need to do is that we have to evaluate the function at 0, the function at 0.27, the function at 0.53, and the function again to 0.8. Once we have these, we multiply these with their respective coefficients, p and 1. We calculate the total here, we add this up, we find the total after we multiply everything, and we multiply them with 3h over 8. 3h over 8 is going to be 3, well, it's b minus a over 8, which in this case is going to be, we multiply this with 0.8 divided by 8. Okay, so this is the Simpsons 1/8 rule, and if we apply this technique here, the answer that we get is the answer is 1.52. Okay, so this is the answer, and again, if we try to calculate the error, for sure, we might expect a way lower error, because it does propagate, like the error for the Simpson 3/8 rule, it has a factor which comes over 6480. And this is just how this is going to change the error. Now, for sure, here you might also expect that similar to the composite trapezoid, composite Simpsons 1/3, we have also the composite Simpsons 1/8. Okay, and what is going to happen next is that these domains that we have, instead of having just 3 segments, we move to 6 segments. And if we have 6 segments, that means that, let's try to figure out how we can have here 6 segments. We take out these coefficients. So 6 segments, we need 7 different points, okay? 7 points, we get here 1, 2, 3, 4, 5, 6, 7. So this is just for the reference, okay? I'm going to write them down. The first point, second, third, fourth, fifth, sixth, seventh. So this ensures us that we have 6 segments in between, and with these 6 segments, we assign what we do, that we pick up the first 3 segments, which are from here to here. So in these 3 segments, we have 4 points, right? And then for these 3 segments, we assign the coefficients which we see in this expression. 1, 3, 3, 1, which means that here we can assign 1, 3, 3, and 1, right? The end point. Sorry, this is not the very best place. Probably I put the 1 here. Then this was half of the integral. Similarly, we move to the other half. We have again 3 segments. Here we put 1 again. This is 3, 3, 1. So the composite trapezoidal rule, the coefficient that we will have to consider will be the following. Actually, let me write them here. The coefficients is going to be, the value initially will be 1, 3, 3, where 2 different regions meet. This is going to be 2, 3, 3, 1. And now this 1, 2, 3, 4, 6, 7, it was just as a reference initially, but now it looks like the composite Simpsons 1/8 technique will have these types of coefficients. And if we add another segment on this side, the other segment, it will be added like this: 1, 3, 3, 1, which clearly make this 2 again, right? And if we add another segment, I guess it is almost obvious that we'll have a repetition of 3, 3, 2s, okay? Which is, again, another 3, 3, 2, 3, 3, 2, And after the 3, 3, 2, so this is 3, 3, 1. If it's going to end here. So these are the techniques that we can use for numerical integration. And these were the, let's say, and let's see an example, actually, let's see. Let's assume that we have let's look at this. That if we have number of segments 0.2 and number of segments 3, sorry, number of segment 2 and 3, let's assume if we have a case where we want to use the Newton-Cote formulas, but we have 5 segments. And the constraint that we have for the moment, so let's remember this is a constraint because pretty soon we are going to jump to a new approach where the segments don't have to be equal to each other. Let's think for a moment, if we have, let's say, 7 segments. If we have 7 segments, but little h's are equal, so all the ranges are equal, what we can do is that we can apply the composite Simpsons 1/3, so we can use 2 segments here plus 2 segments, so using this twice, right? So we get 4 segments. So we find the integral over 4 plus 3. So we use the Simpsons 1/8, okay? So this is one way to put them together. Or let's say that we can have 5 segments. If we have 5 segments, for sure, we can put them together as 2 plus 3. So let's see an example where we can have the same. So if you have 5 segments, then NS is equal to 5, B minus A, this is equal to 0.8, which makes H is 0.16, okay? So let's assume that this is the case, and then the points of interest, there will be the following. We have X is equal to 0, 0.16, 0.32, 0.48, 0.64, and what is left, 0.8. So this makes 1, 2, 3, 4, 5. So we get 5 segments as we expected. So we calculate the values of the function for all these 6 points. So if we have number of points is equal to 6. So it's 1, 2, 3, 4, 5, 6. We index these with I. So we have to find the values of the functions everywhere, and we can use a Simpsons 1/3 rule for the first 3 points. Okay, so here they can be combined with Newton's, and we know that the Simpsons 1/3 rule, the coefficients, they go like 1, 4, 1, right? So we multiply this 1. This will be multiplied with 4, and this will be multiplied by 1. And these values that will be multiplied, this is 0.2, 1.3, 1.74, and then we have 3.18, 3.18 again, and 0.23. So we covered up these 2 intervals, but then we can apply on the other side, we can apply here the Simpsons 1/8 rule. And the coefficients here, they are like what we looked before a moment. They had 1, 3, 3, 1. So we had 1, 3, 3, 1. Okay? So finally, what one has to do, we need to multiply 0.2 with 1, 1.3 with 4. This will be multiplied by 1. And probably, not probably, I guess we should, after we add up these terms, okay, we should multiply the top part with h over 2, okay? And h, in this case, we have to multiply them with 0.32 over 6, which is the whole range divided by 6. And the other expression, so similarly, we are going to use so all of these will be multiplied by the 0.48 by 8. So we are writing these like b minus a over 8. So we add these together, we multiply by this factor, then we add these together, we multiply by this factor, and then finally we add them together. Okay? So if we use this technique, the final integral, it's going to be 1.64. So what we're doing here is simply summation. This is 0.38. And the second part of the integral is going to be 1.26. This is equal to I1, and I2 is 1.26, which comes from the second part, which is in red. We add them together, and we find a more correct value for the integral of this specific function. Now, so these are the classical techniques that we can use for the numerical integration. Now we have a different approach, and meanwhile, do you have any question? Where does 1 over 12 come from? Okay, that's a good question. Lady has a question during the class. Where does 1 over 12 come from? Actually, it can be proven. It's a mathematical proof where the 1 over 12, I guess you are asking about the 1 over 12 at the error calculation, right? So that derivation, it can be easily found out. And this type of errors, they are like generally the errors in error calculation, they are found from the, okay, I see here. Well, not only that, but it's something that in the Taylor series expansion, often the errors, that's where we are going after, okay? We look at the Taylor series expansion because we are trying to approximate something with an lower order polynomial, okay? So that's the traditional approach that we use. But so this is where it comes from. But you need to use a mathematical proof for that. And that is derived from the Taylor series expansion. Now, if you don't have any further question, so let's see. Let me check just for a moment regarding the. Okay, I think we can continue here, but just let me make sure that I'm not sharing the screen. No, I'm not. Okay. So, and then, so what we see here, actually, as the example that we just considered here, the final result, as clearly is asking, this is going to be equal I1 plus I2. So the integral where we separated, we had 5 equally spaced segments or equally spaced points. We calculate for the first range and then for the second one, and then we add up together, and we hope that we get the much better result. Now, what we can do further is that the idea is that the error that we find. So, for example, if we have a look at the errors that we found so far, they were in the order of. Just a second. Now, probably I need some space here. Okay, so now the next topic that we can discuss is Richardson Extrapolation. I left my previous sentence in half, but what we can discuss next is that we can, it looks like we can improve our numerical integration techniques by changing the h, okay, by changing the distance between 2 points. And it looks like smaller the h, better the result gets, or lower the error. So then it looks like we can use an h1, we can use a distance of h1, or we can use a different distance of h2. But they are not equal, okay, so let's assume that they are not equal. So if we have these two h's, we can write the following. We can say that the exact value of the integral, so this is E exact, which we don't know, but we are trying to approach to this exact value. This can be written as the integral as a function of the h1 plus the error of the h1. And similarly, this is also equal to the integral based on h2 plus the error, not based on, but which is a function of h2. And for sure, they do depend on the value of h. And what we can do is that it is easy for us, so it looks like, let's assume for a moment, let's assume that h2 is smaller than h1, okay? If h2 is smaller than h1, then how would you compare the errors? Since this is a numerical integration, we might expect that the error of h2, it is, let me think for a moment. Is it smaller or larger? What would you expect here? How would it compare with the error of h1? If h2 is smaller than h1? So since we get smaller segments, this is going to be also smaller. And this is what we are after. We are after smaller values of errors, okay? And it can be proven that the error of h1, over the error of h2, this is equal to h1 squared over h2 squared, okay? So we can prove this one, but let's check for a moment. So h2 is smaller. Yes, that's correct. So this is larger, this is also larger, okay? Now, so from here, so this is the line of that we follow. And now it can be shown, now from here, it's almost clear the error in H1, this is equal to the error in H2, or approximately, let's say, the error in H2 times H1 squared over H2 squared. Okay? And just for a moment, as we are having this discussion, think for a moment if H2, substituting the values, if H2 is equal to H1 over 2. Okay? So let's assume that we are trying to find the numerical integration, and that given interval, we just cut it in half. Okay? So we just said here that they are different h's. But let's assume that they go like this. If they go like this, here we can get an answer that error using H1 is equal to error using H2 times H1 over H2. What is this? It's going to be times 4. Okay? So it looks like, in case this is equal to this, it looks like the lower error, it will change, it will be improved by a factor of 4 if the ratio here is a factor of 2. So now what we can do is that in this expression, so I want you just to look for a moment, in this expression that we have here, we can substitute for error in E1. So let's have this, the integral, the approximated value of the integral using H1 plus the error in H1. Now, here, instead of this error in H1, we are going to use this relationship that we have here, okay? So that this means that approximated value of the integral using H1 plus the error according to H1, which is error in H2 times H1 over H2 squared. This is going to be equal to the approximated value of the integral using H2 plus the error in H2. So we see here that the error in H2, it appears twice, okay? So we took out one of the expressions, and now what we can do here is that we can try to we can monitor how the error of H2 depends as a function of the two approximated value of the integral itself. Okay, so here we're just trying to construct a recursive relationship between the errors that we get when the h is changing. Okay, but for simplicity, we consider for a moment that let's say that the h is always going by a factor of 2, but we are not stated that there yet. Now the error in H2, it can be written as the difference between these two, so it's H1 minus the approximated integral as a function of H2 over 1 minus H1 over H2 squared. Okay, so this is how the error. So again, let me say, this is the error estimate, okay? This is an error estimate that we try to determine as a function of two approximated integrals for two different step size, okay? So we have two different step size, we get two approximated value of integral, and we are trying to predict this, okay, this error. Now, why are we doing all of this? We're trying to do all of this because we want to use this new, very amazing technique, which can help us to get closer to a better value. And we can simplify this expression a little further, because if we use now, we use this part of the equation, or this identity, and we included with this one here, and we found this beautiful relationship, which we did not have it before, okay? What we can do now is that we can now relate this error expression with the exact value, okay? And this exact value, if we substitute a couple of times so we're trying to prove somehow that if we use two different h's, we can finally find, as a result, that I exact. Okay? Actually, this is not exact, this is still an approximated value, but let's remove the exact keyword for a moment, but that's where we started all of this. The new value of I, we can define this one as this is equal to 4 over 3 times h2 minus 1 over 3 integral using h1. Okay? So it looks like we have to find an integral. Then let's use h1 by using, let's say, composite trapezoidal rule. So the simple thing, we just find trapezoids, we add them together, and we're not doing any more complex thing. Then divide h1 by 2. Most probably, we're going to get a much better result. Then this result, this is called IH1. Okay, this is it's called IH2, where H2 is better. We can combine these two to get a better prediction of the results. So, and the factors that we need to multiply, this is multiplied with 4/3, and this is multiplied by minus 1/3. So this is what this formula is trying to tell. So what we can consider here, for example, let's try to identify, to find a good example. And meanwhile, if you have any question, please don't hesitate. And for this rhombic integration, the things I'm going to share with you just in a moment, a couple of, if we can have a look at the slides. So the value of the integral, we can always try to, so this is the first order of the approximation to get the exact value. Now this one, we can write this one, the general expression is 2 to the power p of the integral of h1 over 2, which in this case, so we are dividing the h1 by 2, minus the integral, which is calculated using h1, divided by 2 to the power p minus 1, okay? So, in this case, we are assuming that if we put here, for example, if we put here p, and what this p is, in fact, is the order of error. So, So the errors that we find in numerical integration, they are of this form. They go from, so this is how the error is propagating. And for this reason, if we put here p is equal to 2, we are going to see that we have here 2 to the power 2, this is going to be 4, divided by 3, so we're just using this one right away, times the integral of h1 over 2, minus 1 over 3 integral using just h1. Okay, so we can use this combination. So, and what we are going to get in one sentence, you can carefully try to follow me here. So, we can use two values of the integral, which are these two, and these two, they have an error of the order OH squared. Okay? This is what they are. They are OH squared. And combining these two, we can find a new expression whose error is now OH4. Okay? So finally, this new expression here, this I, this will be the new integral, will be equal to these two. Again, I'm repeating the same sentence. We can combine it this way. P is equal to 2 because the error is OH squared. So combining these two using this expression, we find this expression which has an error of OH to the power 4. Okay? And now similarly, we can use now these expressions of the error of OH to the power 4, and we can substitute here in this expression when P is equal to 4. If P is equal to 4, what coefficients do we get? We get 2 to the power P, 2 to the power 4 is 16, right? 2 times 2, 4, times 3, times 2, 8, 16. So we get here 16 over 15, because we get this term here, minus 1 over 15, okay? So what do these two coefficients give to us? They give to us, if we have two integrals, I1, I2 that we call them now, these two, they have an error of the order OH4, and this helps us to find a new value whose error is way improved, is OH to the power 6. Okay, so this is how this can be done. And in order to prove this one, we started by writing the error, the exact integration. It was equal to one specific value plus some error. We combine these errors. We also we know the prediction how the errors propagate as we change the h, okay, which is the smallest interval. And something which is very nice about the integral is that when we integrate, we don't make a mistake, or the errors are relatively small. When we differentiate, we have a problem, okay, because not all the functions are differentiable. Now, this is one perspective that I want you to remember regarding the numerical analysis approach, where we have discrete step sizes. Share something. So I hope this part is clear. So we have a couple of values we are using in this way, but now it looks like we can still use a pair of values which both have errors in the order of h to the power 6, and we can improve that further. And finally, what we can construct, probably this part we don't need much, especially this one. I'm erasing also this part, and so Richardson extrapolation, it's a very nice technique. It is very useful, and it helps. You're going to see that it can help us to find or it converges much faster. And the way to think about this one is that we can have a value of the integral. We call this one R11 or I11. So this expression that is given here, in case of this one, we can and probably the best thing to do for this moment is that maybe it's best if we have a look just for a moment. No, maybe I better write this here. So let's say we calculate, let's say we set let's say we give a function, and this function is equal to y is equal to sine of x. So y is equal to sine of x, and we want to calculate the exact integral. And sine of x, when x is 0, y is equal to 0 also. So we can start it like this. So this is y, and this is x. The first thing that we can do is that we can assign initially the h, let it be b minus a. Now, what is this b minus a? What is this value? Sine is equal to 0 when this is pi, right? So this is equal to pi. Let's assume that we start calculating the integral from here. And then, and what is the error here? The error is proportional to, or is O h squared, O pi squared. This is what the error is here, right? Then what we can do is that we can divide this a little further, and we are going to get a new value for the integral, which we call this one I21, okay? Because now this was h1, h2 is equal to h1 over 2, and this is going to be pi over 2, right? And so far, we know how to do this, right? So, and by the way, what is the... Ce o să perdori tudo em partilha para iush, do cap nish classes randomly. Cleida, such integralic to what is the integral using the trapezoid technique when h is equal to pi? So I think, was it Katie? Katie, can you give an answer here? So if we use the trapezoid technique and we want to find the integral of this sine, we know the trapezoid technique, the integral, it's equal to f of a plus f of b times h divided by 2, right? Now, if the endpoints are 0 and pi, what is this? Sine of 0, a, think for a moment, a is equal to 0, b is equal to pi. So, what is the answer here? I want an answer from you.
Should it be pi squared over 2?
No, I want the value of the integral. I get an answer in comment by Nathanael, but think about this one for a moment.
0.
We need sine 0 and we need sine pi, right? What are these two?
Those are both 0?
Correct, they are both 0. But you should not forget that we are looking for the integral, for the area down here, right? So they are both 0, which means that here we get sine 0 plus sine pi divided by 2 times pi. So we get 0. So it looks like the first value of the integral is 0. Is 0. Then, the next step, we cut this in half, we make this pi over 2, and the next value, what is the next value? The next value is, the points are 0, pi over 2, and pi, right? So what is sine 0? Sine 0 is 0, so these are, so this looks like we have 4 values. This is pi over 2. So these are values of x. This is values of f of x. Sine of 0 is 0, sine of pi over 2 is equal to 1, and sine of pi is 0 again, right? And then we're trying to find the integral using trapezoid method again. So what we acquire here, we find that the new value is going to be equal to this and this. Because trapezoid technique, it will have the value of this plus the value of this other. So in a similar way that we did it here. So let's see what we get.
Should be pi over 2.
Exactly, that's correct. But let me check if that's true. This is 1. Pi over 2 is the complete one, right? Because
yes,
this triangle,
complete 1 pi over 2.
This is pi over 2. So we get pi over 2 times 1 over 2. Because the area of a triangle is equal to the one side times the other divided by 2, right? So we get pi over 2 times 1 divided by 2. But we multiply by 2 again because we have two similar triangles, right? So you are correct. This is pi over 2. Now, follow me here and here. So what do we have so far? We have these two values. We have this and this. What can we make use of these in line with the Richardson extrapolation? What we can do here is that we have this value which has an error of OH squared. We have this other integral which has an error of OH squared. Then we can combine these two and find another value which is OH to the power 4. And how do we combine these two? These two can be combined by multiply this with 4/3 minus this 1/3, right? So the next value, we can find the following. We can multiply this by 4/3, and this one comes down with minus 1/3. So what is the result? We have here, the coefficients are these. 4/3 minus 1/3. So 4/3 times pi over 2, okay, minus 1/3 times 0. So we get here 2 pi over 3, right? We get 2 pi over 3. So what is this? We call this one I22. And allow me to erase these arrows here. But for sure, from pi over 2, we get an answer which is 2 pi over 3. Now, this is closer to the true value. Now, what we can try next we can start to divide the interval a little further. Dividing the interval a little further means this. We find here pi over 4, okay, and here 3 pi over 4. Would you agree? So we're just separating this this a little more, and then we need to find the area, okay? And this is going to be I31. This 3, what the 3 stands for, it stands for the number of segments. Sorry, the number of segments. The number of segments, it is expressed as 2 to the power k minus 1. And here, we are increasing k. So, when k is equal to 1, let me think for a moment, so we are increasing k down. So here k is equal to 1, okay? Here k is equal to 2, which means that this is ns, number of segments. This is equal to 2 to the power 1 minus 1. We get 0. 2 to the power 0 is equal to 1, right? And then when k is equal to 2, you get 2 to the power 2 minus 1, you get 2 to the power 1, you get 2 segments, okay? Now, can you see this part of the board? Okay, we'll see. So this is k, this is the number of segments. When k is 1, number of segments is what? Is 1, right? When k is 2, sa segmente kemi ku k është 2?
Kemi 2 segmente.
2, shumë e drejtë, po. Po kur k është 3?
4 segmente, pastaj
Po,
8, pastaj
kjo
kështu.
është 2, në fuqi 3, 2 to the power k minus 1, 3 minus 1, 2 to the power 2. 2 to the power 2 is equal to 4. That's correct. You get 4 segments. And when k goes equal to 4, we get 8 segments because we multiply with 2 each time. So here, we can get I for 1. So this is integral using k1. This is integral using k2, integral using k3, and using integral k4. And we see the number of intervals is multiplied by 2 each time. Good. What does this one mean? This one means that we are at the first possible error level, OH squared. But then what we can do is that after we find all of these, we can combine these two to get this. We can combine these two to get a new value here, which is going to be I32. And we can combine these two to get another I42. Okay? So if we do this, then we can so these are byproducts of the first column. Then we can combine these two to get another value for the integral, which would be I33. And here, combining these two with specific coefficients, we can find here I43. Okay? We have one more contribution. It looks like we can still combine these two and we can get an I44. Okay, so this is Richardson extrapolation, and we can show how this is going to work for us. So, again, yes.
Të janë gjitha errore, domethënë?
Jo, këto janë vlerët e integralit.
Domethënë në bazë të erroreve, apo jo?
Po, e drejtë. So, the first column there are results whose error is like OH squared. Okay, the second column. So if you go down like this, we are increasing k. If we move this way, we are increasing p. The p, if you remember, we wrote like error, it was equal to c p squared plus c1 plus c2 p to the power 4 plus c3 p to the power 6 and so on, right? So here, we increase the p in this direction. But we increase the p in this direction artificially. It's not probably the best correct word, but using a clever technique. So p here is equal to 2, here, then p is equal to 4, p is equal to 6, and so on. So you can see that coming down, we increase the k, which means number of segments, and moving this way, we are using these combinations. But yeah. So I think I can erase this part and also this part, and I hope that this is a little more clear. Now we can move a little faster, which would be the following. So far we have these two values. Now let's try to identify if we use 4 segments. So far in this integral we have this, and this. So we have these 3 values, okay? So we cannot go any further. We cannot improve the error here because we cannot combine this specific value with anything. So let's try to generate this I31. What is I31? I31, it uses the simplest integration technique, the trapezoidal technique, but using 4 segments. Let's see what we get. So we watch here, and pi over 4 is this value. This value. So we're going to get the integral, which is going to look like this. This is a straight line here, this is a straight line here, and a straight line here. So
can we find only the half of the integral and then use the symmetry to find the whole one?
Yes, you are correct, for sure, because it looks like this problem is symmetric. But I'm afraid you won't see too much here. Anyway. I'm afraid you'll not see this part, but we can fix it. If you allow me, I can erase this part because I think it's clear how increasing the k down, we are increasing the number of segments, and p, this is like this. So what is the area here of this little triangle here? This is equal to, what is sine pi over 4? Sine pi over 4 is square root of 2 over 2, which means that this height is square root of 2 over 2 times the other axis, which is pi over 4, right? So we divide by 2, but since we have also this one, this is the correct answer, right? So we keep this, and then this is the area of these two areas. Pra këto të dyja, këto dy trekançat kanë këtë sipërfaqe. Pastaj do gjejmë të trapezin këtu. So what is the area here? The area is here. It is sine of pi over 4 plus sine pi over 2. Okay, trapezoidal method times this distance. What is this? It's pi over 4, right? Divided by 2, because trapezoid is one base plus the other base times height. So we found this area, but since we have to find also this other area here, I can remove out this pi over 2, and we can sum up these two values together, okay? And what we find is the following: square root of 2 over 2 divided by 4. This is square root of 2 over 8 pi plus, here we have pi over 4. You can be faster than me in here. Sine pi over 2, this is 1. No, I have a mistake here. This is pi over 4. This is square root of 2 over 2 plus 1. And who can give me an answer for this one? Who can use the calculator? So is this correct? This is pi over 4. Yes, we have the square root of 2 over 2 plus 1. Okay, so the final answer here, it's going to be square root of 2, it's square root of 2 times 3.14 divided by 8. We get, I get a crazy number, which is, yes, is it correct? So I made a mistake, 3.14 times 1.7, let's approximate this by, no, 1.4 times 1.42 divided by 2 divided by 8, this is 0.5, this is 0.557 plus. Then we move on, square root of 2 over 2, square root of 2 divided by 2 is 0.7 plus 1, it's 1.7. 1.7 times 3.14 divided by 4, it's 1.34. 1.34, and if we add these two together, this is equal to plus 0.557, and this is equal to 1.897. Okay, so this 1.897, it's here, 1.897. So we found this one here. So the next thing that we can do is that we can combine this pi over 2. We can write this one 3.14 divided by 2 is 1.57. (1.57) 2 pi over 3 is equal to 3.14 times 2 divided by 3 is equal to 2.09. Okay, so then we start combining again, but and these two will be combined as follows. We have 1.897, this is 4 over 3 times 1.897 minus 1 over 3 times 1.57, right? So we are going to use these two values to find this. So the result is going to be 1.897 times 4 divided by 3. This is 2.53 minus 1.57 divided by 3 plus is 2.007. Okay, this is what we get. And then what we can do, so let's not forget that what is the error bar here? This is error is proportional to h squared. Here, this column is h to the power 4. Now let's combine these two. But when you combine these two, what are the coefficients? The coefficients, they are 2 to the power p over 2 to the power p minus 1. And here we have minus 1 over 2 to the power p minus 1. So if the error is 4, so here p is equal to 4. What is 2 to the power 4? It's 16. So these coefficients, if we take out this pi, these coefficients, they are going to be something like this. From here, 2 to the power 4, this is 16 over 15, minus 1 over 15. Now, 16 times over 15, we're going to multiply this value because this has a much lower error than the one on top, right? Because this is deeper into the calculations. So this is 2.007, 2.09. This is 2.09. So the answer that we get, it's meanwhile, can anyone find what is the integral of sine x dx from 0 to pi? Can anyone find this one, the analytical solution where this should converge? So what is this? Meanwhile, we can continue like this. This is 2.007 times 16 divided by 15, and we get 2.14, and the rest is 2.09 divided by 15. This is equal to this. The answer here is 2.0006. Okay, so this is how far we can go. And anyone can find the answer for this question here? What is the analytical answer for this integral? Is there anyone who provided the answer in the comment section?
Professor, should be 1, I think. Or
well, let's check. What is the integral of sine of x? It's minus cosine, right? Or am I wrong? It's minus cosine.
should be 2, sorry.
Okay, 2. So it's minus cosine. So here we get minus cosine. Actually, I don't like minus. I always make this plus and change the signs of the integral. So I keep it cosine, and I do it from pi to 0. Okay? So here we have cosine 0. This is equal to cosine 0 minus cosine pi. So this is equal to 1 minus minus 1. So this is 2. You are correct, that's 2. So the correct value for this integral is 2. And with this many steps that we used so far, we found some value which is very close to the analytical solution. Okay? So we can continue one more step by finding here new points such as pi over 8, 3 pi over 8, 5 pi over 8, and 7 pi over 8. So we can divide this further once again, and then we can use the same technique, but if we separate this once more, we are going to find this element, okay? And with this new element, the new thing that we can generate is that with this, we can then find this. And since we have this value on top, we can also get this and also this. So if we separate the interval one more time, we are going to get 4 more different values. And these 4 different values will appear here. And most probably, this will converge, and especially this one, this is going to converge much better to the value of 2. But one thing that we may need to check is that, so to go from the first column to the second column, what coefficients did we use? We used the coefficients of 4 over 3 and the minus 1 over 3, right? We did 4/3 minus 1/3. This was how to pass from this column to here, how to combine these two values to get this. Then the next column, to go from the second column to the third, we used coefficients of 16 over 15, 16 over 15, minus 1 over 15, okay? But then, how can we combine two values in the third column to go to the fourth column? We know that the third column, what is P here? In the third column, P is equal to 6. So we get 2 to the power 6. 2 to the power 6 is 2, 4, 8, 16, 32, 64. So we get here 64 over 63, and here we get minus 1 over 63. So this is the way that so let's assume that here we get a number of 1.9. I'm not sure what we get. But then this means that the coefficient that we will use will be 64 over 63 minus 1 over 63. So this is how these coefficients are going to be used to combine any pair of subsequent values here to get another number for a higher value of P. So this is the Richardson extrapolation, which is a very beautiful technique, and that is used in numerical integration. Now, numerical integration, it's what's next? So we started with Newton-Cotes method. They are not very fun, okay? They are pretty straightforward. You just need to use carefully a calculator, or you can write a code about it. Then we moved on to this Richardson extrapolation, which is really a very nice and elegant technique, because there we use nice steps how we can decrease the error, which is seen that we go to a better error. And by the way, for example, just as a reminder, I'm sure that you already know this, but let's assume that h is equal to 0.1, which is 10 to the power minus 1. So if h is this, if the error bar is in the order of a squared, what is the error? It's going to be 10 to the power minus 2, right? And then, if h is still the same, if we combine two values that have an error of this order, 10 to the power minus 2, we can get a new value, which is in the order of 10 h to the power 4. So we get 10 to the power minus 4. So this is really a very powerful technique with regard to being able to decrease the errors much further. And now, the numerical integration, the next approach is that, the next step that we can follow on numerical integration is to use Gaussian quadratures. So what that stands for, but then we are going to give a break, but I'm just going to say what is next for numerical integration. I hope that, give me another 2 or 3 minutes. So the next step is that we will go after to use spatially constructed polynomials to integrate, to take integrals that can even have singularities. So even functions that even have singularities, we can be able to calculate integrals such as 1 minus x squared from 0 to 1, for example, dx. So these are relatively difficult to figure out, but what we can do is that there are some techniques which allow us to determine, so this will be the function. Then if we are going to integrate from 0 to 1, we can determine some values inside this range for which we just, so let's assume that we determine 2 points. Okay? They don't have to be equally spaced, so things are getting a little more random. But then we have to evaluate this function like an f of x1, f of x2, and just by combining these two, we will be able to find the integral here. For this one, we use a series of spatially constructed polynomials, and these polynomials, they are like Legendre polynomials, Chebyshev polynomials, and when I was a student myself, I was a little scared when I heard about all of these complex types of polynomials, but we know that as long as something is a polynomial, it's not something that we can be afraid of, because polynomials are anything which have x to the power 0, x to the power 1, x to the power 2, and so on. So they are very, very elegant in use, but they have also an extra beauty. And this beauty of these spatial polynomials that can be used is that the first thing, these polynomials, which can be Chebyshev polynomial, for example, Chebyshev. For example, these polynomials, they can be written on the form of P0 of x, P1 of x, P2 of x, and the first beautiful thing is that we can construct a recursive relationship, okay? Which is amazing, because given the first 2 values, we can find the third. Given the second and third, we can find the fourth, which is nice. The second,
Professor,
yes.
when do we finish today?
In 2 minutes.
Okay.
Yeah, we won't do this now, but I'm just giving a few lines of introduction of what can come next. So these polynomials, I can strongly suggest you to go over these. I'm going to share also some materials. But these polynomials, we can construct a recursive relationship. They are orthogonal with respect to each other, and they can be used for numerical integration and many other techniques. Now, do you have any question regarding what we did so far?
Profesor, kam një pyetje në lidhje me detyrat e shtëpisë.
Okay.
Kishim ushtrimin 3 dhe 4 në të